Hello, everybody. Hey, this is going to be a lecture, Static Equilibrium Part 3. Now, in this video, we're really only going to go over one problem in the book, where it's not in the book, but it is very similar to equation or problem number 10. I'm making it a little bit simpler as a way to show you the basic mechanics of this, and then you can make that extension to find the solution to problem number 10 or 11, I think. It might be 11. Anyways, what we have here is we've got a ladder. We've got a ladder that's leaning up against the wall, and it's 3 meters from the wall and 4 meters high, and has a mass of M and a length of L. Okay, so right here, okay, it is about to slip. All right. So we're really just on the cusp. We're on the cusp of slipping. And therefore, we know that we're going to have a force of friction that's pushing to the right. Now, up here, we're going to have the force on the wall, and that is only in the x direction. Okay. We're going to say that the wall is frictionless. Okay, so if the wall is frictionless, then there's no y, right? So we're also going to have a normal force, and we're also going to have a force of mg. Okay, now by me identifying all of these forces, essentially we're kind of going down these steps that I showed you earlier on. We want to read the equation, and basically we are going to try to find the equation for the coefficient of friction. Okay, and so we're identifying all the force vectors. So we've got force of the wall in the x, the force of friction going to the right, the normal force going up, and the weight of the ladder going down. And that's it. Okay, so we're going to choose a convenient XY coordinate system, and that convenient XY coordinate system is just our normal X and Y. And then we're going to wait, and we're going to choose this fulcrum thing partway through this problem. So we want to take a look at just the forces in the X. And we know, as in all of these static equilibrium problems, that the sum of the forces in the X is equal to 0. Okay, so we can see down here that our force of friction to the right, we're going to say to the right is positive, is opposed by the force of the wall going to the left, right? And that equals 0. Therefore, the force of friction is equal to the force of the wall. Okay? All right. So now, you guys, we're going to do the sum of the forces in the y. Now, the sum of the forces in the y, we've got our normal force going up minus mg going down. That's equal to 0. Therefore, the force normal is equal to mg. And we also know that force of friction is equal to mu mg, okay, which is mg is our normal force. So we can say that mu mg, force of friction, okay, which is mu force normal, is equal to the force of the wall. Okay, so we're looking for this. We don't know what that is. We've run out of equations, and now we are going to do the sum of the torques. And this brings us to problem number 4, or step number 4, and that is to choose a fulcrum. Now, you guys, we can put a fulcrum wherever we want. And we talked about the fulcrum as being the point about which something rotates. And it's really pretty arbitrary because we can put an imaginary fulcrum anywhere we want. But there's really only 3 places that we want to put it. We want to put it under here, here, or here, because those are the critical points. We've got a force there, a force there, and a force there. We actually have 2 forces right there. And when we're doing our torques, because torque is equal to force times our perpendicular radius, if we put our fulcrum right here, here, or here, then the radius to that fulcrum is going to be 0, and one of those values is going to cancel each other out. All right, for our purposes, I am going to put our fulcrum right there. Okay, now that means that this force and this force are going to have 0 torque because we put it at a radius of 0. Okay, so now we want to do, the sum of the torques. Now, the way to imagine torques and what the equation is, if our fulcrum is here and we were to, for example, get rid of the wall, we're going to get rid of this force, we would see that due to the force of gravity acting from the center of mass of the ladder, it would rotate clockwise. And by the same imagination here, this force of the wall, okay, this would cause a counterclockwise torque. So this clockwise torque and that counterclockwise torque are going to be equal and opposite. All right, so torque is equal to FR sine theta, okay? And for our first force, and I'm going to go with this force, the clockwise force, our force is mg, okay? Our radius, the distance from here to here, is half the length of the ladder, because that is where the center of mass is. And we can think of all of that force acting right in there in the center. So that's our force times our radius. And now we're going to take the sine of the angle. And this angle right there is going to be theta. So this angle right there is going to be theta. And we can see that this is a 3, 4, 5 triangle. So we could put in 37 degrees there. Okay. 37 degrees. You guys, to calculate that, we're going to say inverse tangent of opposite over hypotenuse. So the inverse tangent of 3/4 happens to be 37 degrees. All right. So now we're going to say minus. Now we're going to have the force of the wall, okay? And the distance from here to here is going to be L, okay? And that angle right there is going to be, essentially, you guys, we want this perpendicular one, and that is going to give us L cosine theta. And our theta is 37 degrees, okay? Now, because it's all equal to 0, we can make them equal to 0 here, and we can see that the L will cancel out, and we're going to divide by the cosine of 37 degrees, and we can say that the force of the wall is equal to mg tangent of 37 degrees divided by 2. Okay, now you guys, that's exactly what we needed in order to come up here and substitute it in right there. All right, so I'm going to take these two, okay, and I'm going to set those two equal to each other. So we're going to have mu mg is equal to the force of the wall, and we know the force of the wall is mg tangent 37 degrees divided by 2. And now we can see that the mg's cancel out, and we're going to get mu is equal to the tangent of 37 degrees divided by 2. which happens to be, you guys, the tangent of 37 is 0.75 divided by 2 is going to be 0.37375. And that would be our answer. Okay, so for problem number 11, which is, this is kind of the slightly simpler version of that. We're going to have a firefighter, okay? We're going to have a firefighter that is going to be climbing up the ladder, and that's going to add another force, and it's going to add another torque. But based using this as a base model, you should be able to work your way through problem number 11. Okay, now you guys, there is going to be on the test, there's going to be using calculus, find the center of mass of a rod. Now, this is the example that I did yesterday or in the previous video. And if you are unfamiliar with that, this is really an easy question. You just need to come find me and I'll go through it, or you can just look at my example from the last video, and that's going to be straight up. There are more complicated examples of using calculus to find the center of mass. And that example is problem number 6. You guys, I will do another video on problem number 6 on how to do that. And you can see that it's going to be a little bit more complicated than the answer to the finding the center of mass of a rod. Okay, but until then, we will see you soon.